Welcome all. Today you will need pen and paper. This is going to be a bit of an experimental lecture. We will talk about natural gradients, what they are and why they are useful in the context of neural network optimization. So why bother? I can give two reasons. One is that if you plot a training error or test error as a function of the number of training epochs, then a typical pattern that is observed is the following. We will have some kind of decay of standard gradient descent. And we often see a much faster convergence of natural gradient descent. Now, why doesn't everybody use natural gradient if that is the case? The reason is that a single epoch is much more expensive in natural gradient descent. So if you put here not epochs but wall clock time on the x-axis, then things look less favorable. However, it is still an open question of what will work better in the long run. And the second reason why it's worthwhile looking at natural gradients is that many methods like batch normalization or specific activation functions like the exponential linear unit are motivated either in advance or once they have been found out to work well post hoc as approximations of natural gradient descent. So many optimization tricks turn out to approximate natural gradient descent. This field was founded, so it has been understood by many. It has been natural gradient has been invented in several fields, but it is associated with one name in particular, namely with Amari, who has spent half his life popularizing the concept. And it is a concept from so-called information geometry, which lies at the intersection of differential geometry and statistics. So a field called information geometry. And this is something popular with physics, with physicists, because they understand it. Yeah, differential geometry plays a great role in relativity and so on. So they like to indulge in this. Okay, so what's wrong with standard gradient descent? I want to start by revisiting standard gradient descent and then see that it has certain not so desirable properties which are addressed or improved upon by natural gradient descent. So standard gradient descent can be justified as follows. So we have a parameter update I start by repeating what it is. Yeah? So we find new parameters by starting at the old parameters and then having some magic step size times gradient of the loss. So the loss depends on the parameters and on the training set. And I'm here using the convention that this gradient is a row vector, which then works out better with the Jacobians and so on when we do backpropagation. And this simple recipe can be justified via a method called proximal gradient. In proximal gradient, we start by looking for a vector which, on the one hand, is aligned with the greatest possible loss reduction that we can achieve. So we try and find parameters theta star, which on the one hand try to follow the direction which will reduce the loss most. We have just a vector product here. But on the other hand, we also have a retaining potential which says we don't want to walk too far from where we started. So we have this is a harmonic force with a stiffness here of 1 minus mu. And then we have a quadratic term that binds theta star to our old or previous parameter estimates theta t. And if we solve this quadratic problem for the optimum theta star, then we find exactly the formula above. So the second term here would be the prox operator. So if we have, as you see, it's just a harmonic potential in some parameter space. And where's the problem here? The problem is that there is some arbitrariness in how we parameterize a statistical model. Let me illustrate this. So let's look at the simplest model that we can imagine, just linear regression. Okay, there are so many ways to parameterize this. I could say here that my output is a slope A times some input X plus some offset, or I could have some Eulerian form. I could say that I have some vector W transpose times X and O minus some number C should be 0. Excuse me, so this is a 0 and this is an O. And there are so many other ways. Now, if we take, and let's here constrain 1 to have unit length. Now, if we look at the family of all possible models here, so if we take all possible values, we can have A and B on the real line, and C is also arbitrary. The families are the same. It's just all conceivable linear regressions that we can imagine. Same family of models, just a different parameterization. And I now want to make an argument not about linear regressions, but about an induced distribution over outputs and how that depends on these parameters. Yeah? So let's say we have some input distribution P of x. And because we are discussing neural networks here, I can easily, so there's a cheap way of turning a neural network into a probabilistic method, namely by just letting the output neurons be probabilistic. Yeah? So we have a neural network with a probabilistic output. So for classification, for example, I could say that we have a distribution of some random variable z conditioned on some input x, and that would be in a two-class classification problem a variable which is Bernoulli distributed with a chance of success given by O. O is the deterministic output of the neural network. And this O in turn depends, of course, on the input and on some parameters which we may have. And this will give me some probability mass function, which I can write as P of z given x. For regression, which is a better match for the linear regression problem I've shown above, our z distributed x would be given by a normal distribution with a mean, again, given by the deterministic prediction of the neural network and some variance that I can choose. And this now has a probability density function P of z given x. So here for binary classification, z is in 0, 1, and here z can be anything on the real line. Okay. So in this sense, I can say that for each input, my neural network induces a distribution over possible outputs. And how, this choice of distributions, how does that relate to what we normally do by minimizing loss and so on? It's like in classical statistics. Yeah? You can either simply say, I want to minimize the sum of squares, and this will give me my best linear model fit to my data. Or I can say, I can make this more probabilistic argument and assume that my measurements have a certain error distribution, for example, a Gaussian one here in regression, and I want to find the maximum likelihood solution. So just to do this once, I will relate this to the loss that we usually discuss in neural networks. We have some likelihood, which for a given training set would be a product over all the samples that we have in the training set. And then I have some ground truth targets. And I'm looking at this conditional probability of my ground truth targets given my inputs, and that depends on some parameters. I could have written the parameters up here explicitly if I had wanted. Okay, instead of working with a likelihood, it's often more convenient to work with a negative log likelihood. And then my product turns into a sum. I have sum over minus log of these probabilities here. And this log of these output probabilities, this is what we usually use as loss functions. So that would be the loss that we usually have between some ground truth Ti and some output that I obtain from a given input and a given set of parameters. And this is the empirical risk that we usually minimize when we train neural networks. So this is also the justification why when we train, let's say, a foreground-background classification problem, why we're not using the squared loss, but why we're using cross-entropy. Because for foreground-background, the Bernoulli is a better model than the normal distribution. And the opposite argument goes for regression. So here's the connection with what we usually do in neural networks when we don't think about a probabilistic argument. But what we get overall here is a distribution of outputs, or a joint distribution of outputs and inputs, P of X and Z, so comma, because I'm talking about the joint distribution here. And this is probability of Z given X times P of X. And P of X, there's nothing we can do about it. So this is just given by the world. So these are the training inputs. And the only thing we can influence at train time is this second term here. So our conditional distribution over outputs given some input. Okay, and let's look at this thing now. So P of Z given some input X, and that depends on some parameters theta, is a family of probability distributions. And when we want to address a specific member of this family, we call it by its name. The name here are the settings of the parameter values. So going back to the linear regression example I gave above, the probabilistic model that we have in linear regression is that we say that we have a probability of outputs z, which is given by a normal distribution, and the mean of this normal distribution is given by, so we have a normal distribution, so z given x here is a normal distribution, and the mean of this normal distribution is given by the output of our network, which depends on the input and the parameters. And then we assume here some standard deviation for these normal distributions. Okay, so each linear regression model gives me this family, or gives me this output distribution. And if you specify some distribution over inputs p of x, this gives me an overall joint distribution of inputs and outputs. And the point now is, no matter how we parameterize this linear regression model, if we use slope and offset, or if we use, there are so many ways to parameterize. I could use here the angle and offset, or I could use the normal vectors. No matter how we parameterize this linear regression model, I always obtain the same output distributions. However, in this linear regression model, we can only have two independent parameters. So, in other words, this family of probability distributions lives on a two-dimensional manifold. And the choice of parameterization gives me the coordinate system on this manifold. So what I've been trying to sketch here is the Riemannian manifold of probability distributions that can be realized by some model. And this Riemannian manifold, that's fundamental to the model. Okay, so for example, let me sketch a tiny neural network. Let's say this is the neural network here. I do have freedom in how I want to parameterize the perceptrons, but this model here corresponds to one specific NeuroManifold. So let's say I have a total of 9 parameters, because each of these perceptrons has 2 inputs and 1 bias. Yeah? So this thing here spans a 9-dimensional manifold, or NeuroManifold. If, on the other hand, if I now add a perceptron, this thing now spans a 12-dimensional manifold. That's not right, because this one has, so this is 3, 6, 9, and 4. This is a 13-dimensional manifold, because my last perceptron now has a total of 4 inputs. So by choosing a neural network and by saying, which neurons we want to have and what connections we want to have between the neurons, this is a fundamental decision. This will define the family of possible outputs of the model. But then how we parameterize the individual units is arbitrary. So in other words, I have some coordinate system here, let's say this is, just for the sake of argument, yeah? Let's say this is parametrization in terms of slope and offset. But I can have some different parametrization, and sometimes these can be very non-linearly related to each other. This could be a parametrization in terms of, let's say, the Euler normal form. So the manifold stays the same if I choose a particular statistical model, and the parameterization that I choose defines the local coordinate system that I use in this manifold. So the manifold is fundamental, but the coordinate system is not. And again, why bother? Because up here, scrolling back up, our prox operator is given in a specific and in fact an arbitrary coordinate system. So let's, I'm going to flatten the manifold here just because it's easier for me to draw. So for example, in this blue parametrization here, my prox term, let's say around this point here, is going to be a, a nice isotropic parabola. But if I'm using the identical, so I'm showing here the identical manifold, but a different parametrization. Let's say I'm just using an affine transformation here. And I should start at the same point. So the point in the middle, let's pretend is this point here. And now my prox operator will look like this. So in other words, my gradient descent will give me a different direction. So even though the loss function, this is maybe surprising. After all, what did we want to do? We started from some parameters and then picked new parameters so as to follow the direction which minimizes the loss. And it so turns out that the direction which we then truly follow depends on the arbitrary parameterization that we use. So in this sense, gradient descent is not innocent, or the particular direction that we choose is tainted by this arbitrary choice of parameterization that we used. And this is, of course, a sorry state of affairs. So we would like to abstract from this arbitrary choice. We want something that is independent of whether I use slope and offset or a normal vector to specify the way my linear regression model looks. And this is exactly what the natural gradient allows. So this family of possible output distributions, this Riemannian manifold is also called NeuroManifold by Amari. It's a fancy name, right? Next time you write a novel, this could be a title. The NeuroManifold. Is a Riemannian manifold, and to those who know about differential geometry, what we want to follow here is a covariate gradient. So we need the metric tensor of this Riemannian manifold. And the metric tensor happens to be given by the Fisher information matrix that we will derive in a few minutes. So just out of curiosity, who knows what a metric tensor is? All the physicists this is essentially a question of who studies physics. Okay, so not so many people. Okay. Good. Go ahead.
Sorry. So in the case of, just wondering again how I can imagine this manifold. So I guess the simplest case would be if we have a neural network that just has one perceptron, so it has one weight and one perceptron, so it would be a 2D manifold. And so I could, for example, parameterize it just by W and by however I do the perceptron, right? The right. And then what would the curvature even mean in that, for example?
So okay, so let's say we have a simple statistical model which gives us a normal distribution, and the only parameters that we have are the location and the spread of the normal distribution. And even for an innocent normal distribution, I have different ways of parameterizing it, because the way we usually do it is to say we have some x minus mu like this, but I can have other ways. For example, I can now multiply out this square expression and then have different coefficients associated with the terms of my polynomial. And so this family of normal distributions in this again is a 2D manifold, because I have fundamentally two parameters. And now there are other models which it would be, or other distributions which could be desirable to fit. So maybe I would really want something, let's say, that is square. Or I would like to have something which is a bimodal distribution. And these live outside the manifold. So maybe the square lives here, and maybe the bimodal distribution lives there. So if we have a small model, this traces out a very low-dimensional manifold in the space of all conceivable probability distributions. And you ask, why is it not a plane? So why is it not a surface? And I can ask, why should it be a surface? But maybe somebody can give a better answer than that. Yeah.
So I think a good example is that if you imagine two Gaussians, for example, that are very close to each other with a high standard deviation, so they are overlapping, then they are essentially, they look as if they're almost the same. So it's really hard to tell if I have a mean of 1 and 1.001 and a standard deviation of 1 or something, then they're almost the same. So on the manifold, they would be very close together. But if I had so the same mean, but a much smaller standard deviation, so that they're essentially peaks, then they would be much further away from each other. So in that way, actually the distance between, so if I just imagine those being represented by a single point somewhere on that manifold, then the distance between those two who are very close to each other would be really small. Sorry, the one with the big standard deviation would be really small, whereas the distance between those which have a very small standard deviation would be much, much larger. And effectively, that means that it wouldn't be, because it would be a plane, it should always be the same. It would be the same distance, because I would just, because the points would be at the same distance essentially. But if it's not a plane, because the distance between those points essentially is larger depending on where in the parameter space I am, so it essentially becomes a somehow curve essentially. And I can send around a blog post where they're essentially using that example and coming from that.
But shouldn't you always find a reparameterization if it's not a closed extent that in which you can transform it such as isoplane?
Let me give a different answer, okay? I thought of one. So let's look at this point and at that point which lie on the manifold. Yeah? And let's say this point corresponds to a Gaussian sitting here, and that point corresponds to a Gaussian, let's even use the same standard deviation, a Gaussian sitting there. And if I now take the arithmetic mean between the two, so I connect them by a line and I pick the intermediate point, then if I just add these distributions, if say I take the first distribution plus the second distribution, so 1/2 times the first one plus 1/2 times the second one, I get a new distribution which now is bimodal. And the bimodal distribution I cannot, of course not represent by any single Gaussian, so it must be off the manifold. And this shows me that the manifold is curved. Okay?
Okay, that makes sense.
And yeah, ask more questions, please. Yeah.
For the proximal gradient formula, what is the second term mean? Is it the penalty term?
Yes. This is like the first term is go find a better place, and the second term is don't venture too far. You see, this is a cautioning term. Because, so, this eventually translates to the step size. Yeah? Because this says something about how strongly curved do I expect my loss surface to be. So I know in which direction it is better to go, but I don't know how far to go. And if I go too far, I will overstep the minimum. I will overshoot the minimum. And this is why there is the second term, which is don't walk too far from where I am right now. More questions? Yeah?
How the loss, the direction changes depending on the parameterization?
Can you say it louder, please?
Why is it that the direction at which we move with gradient descent changes with the parameterization?
Why does the direction which we move change with the parameterization? Because in terms of differential geometry, the parameter itself is contravariant. So that means, well, I'll say no what it means. And the gradient here is covariant. And if I add up a contravariant and a covariant thing, then I'm looking for a weaker word, not catastrophe. Well, then trouble ensues. Yeah. So what does contravariant and covariant mean? The simplest example is if you simply have a scaling of one of your axes. So let's say we have some parameter, and the units of this parameter are kilogram, and then we have a different parameterization, the units of which are gram. So there's a factor of 1,000 between the two. And if I now want to change from one parameterization to the other, in gradient descent, I always start at some point and then I walk to the next point and walk to the next point and so on. Yeah? So let's say this is theta 1 at time 1, this is theta at time 2, this is theta at times 3. Now when I change the parameterization in my model, and if I want to start at the same effective model, then, for example, if my initial setting of the parameter was 1, so I started with my parameter being set to 1 kilogram or 1 meter per square second or whatever, then I need to start with theta tilde equals to 1,000, yeah, to get the same effective model. And that means as I changed my parameterization, I also had to change the value in a corresponding fashion. And position vectors, location vectors, or parameter vectors are always contravariant. Yeah, so you correct for the scaling or squeezing of a particular axis. The gradient, on the other hand, behaves differently, and because the units are in the numerator instead of the denominator, yeah, if you look at the definition of gradient, and this is why it depends on the specific parameterization. Yeah, this would be my answer to your question starting from this formula here. My answer to your question starting from the second formula would be the picture that I've shown here on the side. Yeah, so I have some restraining term, but the shape of the restraining term depends on the parameterization, which is arbitrary. And hence, my overall descent direction will be different between the two cases. More questions? Yeah?
Can you once again explain in which space this manifold lives and why adding points on, like in this space, corresponds to adding the corresponding probabilities?
Down here.
And actually also why the manifold mode should be like locally homomorphic to,
yes,
to like R to the N and so on.
Okay. So it can have singularities. However, if you if you take, let's say, a planar network with a sigmoidal activation functions, let's say, then as you change one of the parameters infinitesimally, the distribution over outputs changes infinitesimally. And this tells you why the manifold is connected. Yeah? What is the space in which it lives?
Like a space of all probability distributions that exist?
Yeah, that is correct, but I don't know if that satisfies him. So,
metric space. Kind of structure.
I mean, also, isn't there like infinitely many like distribution functions that are like
Yes, so especially because we can have continuous inputs. This already tells you it's it's infinitely. So you want to know what is it a metric space or not? And
yeah, I mean, when we say it's a manifold, we of course say something. It has a lot of structure. We can somehow picture it, and we know what we work with. But when we don't even can specify the space in which it lives, then what's saying it's a manifold is kind of void statement.
It's the space of probability distributions, like he said.
Okay.
So
Is
non-negative functions integrating to one.
and does the space have a topology, or some sort of structure? I mean, obviously I can add functions as you did. That's something.
Okay, I cannot answer your question. I need to think about it more. Yeah? Maybe questions that I can answer? No questions that I can answer. Good. Okay, good. Yeah.
A little bit misleading in this example is that it looks like it's just a three-dimensional space, and so these two other probability distributions are just either below or above, which is obviously not true. Right?
Yes.
Infinitely.
Yes.
Space.
I just have trouble drawing these.
Yeah, of course.
No, thanks for pointing out. Yeah. Okay, good. So let's have a break, and then after the break, I will argue that the Kullback-Leibniz divergence is a good, will give us something that helps us compute inner products between vectors, and that can be used to get a metric tensor on these manifolds. But let's have a break first.